Let me see. Okay, my video is on. Yes, it's on. All right. If you look at the web page, you can go to calendar. Okay. We have let me look into this. Test is on October 11th, not. Okay, if you look at the calendar. I'm clicking on it. Test is on October. Okay, let me see. September 14, we have October 11, right here. So we have 2 more days to go over chapter 3 and 4 questions. Then we're going to have a test on, right? On the test day, when you come to Zoom meeting, I give you a passcode. Then you click on chapter 3 and 4 test here. All right? Chapter 3 and 4, then take the test. So I'm going to go back to my PowerPoint chapter 4 slide at quantifying carbon. We talk about, last time we talked about a car in the United States produce its own weight in carbon every year. We were talking about a lot of carbon emissions from deforestation and burning fossil fuels, transportation, etc. Now, today we're going to focus on more about scientific method, how we do a measurement in chemistry. Okay. When you do measurement in chemistry, a measurement with numbers are expressed in the format that shows uncertain digit. Uncertain digits in 65.2 is the rightmost number, which is 2. In 255.345, uncertain digit is in red. Okay. This has 3 significant digits, including all the numbers, all the uncertain digit and the other numbers. So let me go back to slide presentation. Hold on a second. Okay, these 2 numbers, when we report as a measurement, we don't show unlimited number of digits, numbers. Only we round it off to significant digits. I'm stuck in here. Let me see. Now, in a measurement, significant digits include uncertain digit and other numbers to the right, to the left. Therefore, this number 65.2, all the non-zero digits included is 3 significant digits. Therefore, measurements expressed as numbers have significant digits, figures. Sometimes we call it digits, significant figures. The second one has, including uncertain digits at the right, 5. Count all the rest of all numbers to the left. You have 6 significant digits. So it's easy to get the significant number, digits or numbers or figures in a measurement. Let's see some examples. Getting significant figures. All non-zero digits are significant, as we shown in the previous slide. For example, 1.55. Uncertain digit is 5 to the right. Including that, there are 3 significant digits. All zeros embedded between 2 non-zero digits, like here, are significant. Therefore, this 0.1003 measurement has 4 significant digits. All right. Trailing zeros is in a number when decimal places followed in the decimal places. For example, decimal place here, 1,000, no, 1.00. All are significant, including all numbers. Zeros in the decimal place are significant. But zeros in whole numbers, trailing zeros in whole numbers are not significant. After the decimal place, it's significant. Leading zeros are not significant in any number. Leading zero in 0.00305, leading is the now zeros in front of 305, they're not significant. Therefore, you only count 3, 0, and 5. Therefore, see 3 significant digits in the number. Now, if you do some examples, I'm going to do it. For each of the value below, determine the number of significant figures. First one, what do you think? 100.0. That 0 after decimal place is significant. Therefore, all zeros are significant. It should have 4 significant digits. In the second one, all 3 numbers are significant. In the number C, leading zeros are not significant. Therefore, only the 1 significant digit in 0.001. In the D, there are trapped zeros or zeros in between non-zero numbers. So there are 4 significant figures. Now, other thing you need to know is about measurements. When you calculate something using 2 measurements, the answer should be rounded off to certain significant uncertain digits. That's what we're going to look at in significant figures in calculated answers. In addition and subtraction, when you add 2 measurements, like the 1.003 plus 0.2 plus 0.001. Okay, if you look at this, in addition and subtraction, you look at the decimal place. The lowest decimal, the first decimal place here, second decimal place, third decimal place. Which decimal place has the highest uncertainty? Second decimal place has the highest uncertainty. Therefore, you keep the decimal place at the highest uncertain level. That answer should be rounded off to first decimal place. Do you see that? 1.2, you had to round the number to first decimal place, which is done here because you keep track of the lowest, the decimal places with higher uncertainty, then you do that. Okay, let me go back here. Do you have a question about this? When you're adding and subtracting material measurements, you round the answer to the decimal place to the left, most uncertain decimal place is the first decimal place here. That's how you round it off. In multiplication and division, which are similar, you don't look into decimal place, uncertain decimal place. You directly look into significant figures. This number has 4 significant numbers. This one has 1. This one has 1. The answer is 0.005 when you multiply it. So this answer should be rounded off to one significant figure. Therefore, this one has one significant figure. This one has one significant figure. This one has 4 significant figures. Therefore, answer, you don't write down any number after one significant figure. Therefore, the answer's uncertainty or the significant figures are decided by one with the lowest significant figure. Let's do the calculation right like this. This one is a division. Both has 2 significant digits. Therefore, this calculated answer 16.129 should be rounded off to 2 significant digits. 2 significant digits is 1 and 6. Then you round off to 16. If this 1 in the third decimal place, if it is 1 was, this 1 was 5, then you add a 1 to 16, it becomes 17. In the multiplication here, there are 3 significant digits, 1 significant digit. Answer is this. The answer should have 1 significant figure. Okay, therefore this number is 1 significant figure has. If you put a decimal place, it becomes 4 significant figures. You don't put a decimal place after 5,000 to keep up the significant figures in calculation. Okay, the next one, addition and subtraction. Number, the C, 1.003 plus 0.01, you add them up. You have to round out of this to second decimal place, right? We talked about this most uncertain decimal place. So therefore, it should be rounded off to second decimal place. So 3 is less than 5. Therefore, you don't add 1 to the second decimal place. And the answer is 1.01 with correct decimal place. In subtraction, if you look at that, most uncertain is first one has in the third decimal place. Second one has the uncertainty in the first decimal place. The answer here should be rounded off to first decimal place. Therefore, you drop all the zeros. You don't add anything to 9 here because 9, the next number to 9 is 0. If it is 5, you add 1 to the 9, okay? So that's how you do figure out significant figures in calculations. Now we're going to look into more molecular structure, going back to chemistry. We go now Lewis structures. Molecular formula is not showing any connectivity between CH4 and methane. But we can write down structural formulas and show how atoms in CH4 are connected. For example, the first two Lewis structures are structural formulas. It shows the structure connectivity. They've been written down to follow the octet rule. We talked about that before. So carbon has a octet of electrons, 4 bonding pairs. Now to predict the geometry of the methane, connectivity is shown in the Lewis structure, but what exactly angles are between these carbon-hydrogen bonds are not shown here. So what you do is use a model called valence electron pair repulsion theory that we're going to talk about in the next slide. When there are bonding electron pairs, they repel on the central atom to create a structure where all 4 bonds are distributed in space equally away from each other. That kind of arrangement is called tetrahedral arrangement. So according to valence shell electron pair repulsion in Lewis structures, there are 4 bonding electron pairs. So structure is tetrahedral. In the space filling model, electron distribution also takes up tetrahedral shape. So if somebody said something, okay, let me go back to valence electron pair repulsion theory, where we use the bonding and non-bonding electron pairs in the central atom, giving certain bond angles between the central atom. Central atom decide the shape of the molecule, molecular geometry. This is foil bonding electron pairs. They are repelled, electrons repel around the carbon atom. Therefore, you get the tetrahedral arrangement. A tetrahedral shape molecule has bond angles of 1095. You probably heard about this tetrahedral before. Now let's look at another example, ammonia. Ammonia Lewis structure, when we wrote it, we got this Lewis structure. It has 3 bonding electron pairs and a 1 lone pair. The central atom is the one that decides the molecular shape or angles in the molecule. They're like methane. 3 bonding electron pairs and 1 non-bonding electron pair are distributed around the central atom in a tetrahedral arrangement. This is one of the bonds. There's no atom attached to non-bonding electron pair. The non-bonding electron pair has more electron density centered on nitrogen. Therefore, they repel other 3 NH bonds. It deviates from 109. This should have been 109 around here. Therefore, ammonia molecule has slightly lower bond angle than methane molecule. This shape right now is not tetrahedral. When the shape is decided by the way atoms are bonded to each other. Therefore, it is trigonal pyramid shape. So when you have one lone pair and 3 bonding electron pairs, you get trigonal pyramid shape. So looking at Lewis structures, you can tell the molecular shape. Bond angles, according to this theory, VSEPR theory, ammonia has 107 bond angles. Methane has 109. If you look at water, when you write down the Lewis structure of water, the central atom decides the molecular shape and bond angles. Oxygen has 2 bonding electron pairs and 2 non-bonding. So these 4 electron pairs, including non-bonding, 2 non-bonding and bonding, are distributed in the space, just like methane molecule. But these 2 lone pairs of electrons have more pushing power than OH electrons, bonding electron. Therefore, it's squeeze the 109 angle even further than ammonia molecule. If you look at the molecular shape, you're not looking at the lone pairs. You're not looking only at the framework of bonding electron pairs and the bonds. The molecular shape of the water is called bent shape. So we can go through some of the examples looking at central atom in the Lewis structure. We can predict the shape and the bond angle. Carbon dioxide has 2 atoms connected to central atom carbon. Electrons in the two bonds push apart as far as possible. This is the Lewis structure of carbon dioxide. If you look at here, this double bond on the carbon behave just like a single bond in methane molecule. There are two bonding electron pairs. There are no non-bonding electron pairs around the carbon. Therefore, repulsion is between two bonds. Therefore, it creates a linear structure. When two things are in space, distributed around the carbon atom, so it forms a linear shape. The shape of the carbon dioxide molecules is linear. The angles between carbon and oxygen bonds are 180. So we have different shapes, different angles based on the valence shell electron pair repulsion theory. We're going to summarize this molecular geometries. As we discussed, carbon dioxide has a linear shape. It has two bonding electron pairs between carbon and oxygen, equally distributed in space, therefore 180 angle. In water, you have two bonding electron pairs and two non-bonding. Non-bonding electron pairs pushes the bonding electron pairs further, angle is 104. In a molecule named BCl3, the third one, it has, in the Lewis structure, it has three bonding electron pairs, no non-bonding electron pairs. When three things are equally distributed in space, it's a trigonal planar. In a plane, there are three electron pairs, bonds with 120 angle. Three bonding electron pairs and one non-bonding pair of electrons, like we discussed in ammonia, is called trigonal pyramid. That's a pyramid here. In the methane molecule, we have four bonding electron pairs, no non-bonding electron pairs. Therefore, methane molecule has 109. So we're going to look into different geometries. Carbon dioxide has linear geometry, two double bonds similar to one single bond are distributed in carbon dioxide in a linear way. In ozone also, we talked about ozone. If you look at the Lewis structure, one of the Lewis structures, that double bond is same as single bond. There are three electron pairs around here. Lone pair, another double bond and single bond is same almost. So three electron pairs gives the structure of the ozone to be bent, just like water. And water also has a bent structure. So therefore, bond angles could be predicted in bent molecule. For three atom molecules, if there is at least one lone pair, just like here and here, the central atom geometry is bent. This is bent geometry. This minimize the lone pair, minimize the repulsion between lone pair and bonding electron pairs. The molecular shape and the bond angle governs the physical and chemical properties of these molecules. We're going to look into how the greenhouse gases differ from non-greenhouse gases based on the geometry of the molecules in a minute. Predicting the molecular shape, we're going to do a few problems. Excuse me. Carbon tetrachloride is tetrahedral. When you write the Lewis structure, carbon is the central atom, chlorine is the terminal atom. You add up all the valence electrons and come up with the Lewis structure here. You fill octet to carbon and chloride also has octet. All these electrons are same as total number of valence electron in carbon tetrachloride molecule. The shape is tetrahedral for carbon tetrachloride. Why? You look at the central atom. Normally, to get the molecular shape, we look at not the chlorine, central atom. In a structure, center decide the shape, okay? In this chlorofluorohydrocarbon, Freon 1, 2. When you, carbon atom is the central atom. Therefore, there are 4 bonding electron pairs. Therefore, it is tetrahedral, okay? So they are equally distributed in space. In hydrogen sulfide, H2S, it's like water. So there are 2 bonding electron pairs around sulfur. In the periodic table, sulfur and oxygen is found in the same group. Normally, H2 has bent. H2S is similar to water. It also has bent geometry, similar argument. Because the Lewis structure is same for water and the H2S, having same number of valence electrons. So predict the shape of the molecule. Predict and sketch the shape of the molecule. Sulfur dioxide. When you write down the Lewis structure, it has 1 double bond and a single bond. Double bonds are almost equal to single bond. Double bond is considered as a single bond. Therefore, just a bond, 2 bonding electron pairs, 1 non-bonding. This should be bent. This is just like water, 1 and 2 bonding electron pairs. So it's like ozone. Ozone also had the bent molecular structure. If you look at sulfur trioxide, it has a trigonal planar. When you write down the Lewis structure, it has a double bond and a 2 single bond. Double bond is treated in VS EPR theory same as single bond. 3 single bonds. Like in the BF3 molecule, BCl3 molecule, we talked about common geometries. 3 bonding electron pairs here. It's 120. 120 in a plane is called trigonal planar. So that's how you predict the shape and the angles found in molecules. Now we're going to look at some aspects of covalent bonds. Some covalent bonds are polar covalent bonds. There's a polarity between bond making the molecule. For example, HF. HF, when you look at HF, fluorine has a greater attraction to bonding electron pair than hydrogen. Therefore, in the bond, electrons are attracted more towards fluorine. Okay? So therefore, polarity is created. There's a slightly more negative charge on the fluorine and little positive charge on the hydrogen. So it depends on the electronegativity difference. Electronegativity of fluorine and hydrogen need to be compared to find out exactly how much polarization takes place. Electronegativity is a number that are shown in the periodic table in the diagram here. If you look at the periodic table, if you go down a group, electronegativity decreases. These numbers decreases. If you go in across the period from lithium to fluorine, it increases. At the top right corner, except we are not talking about noble gases, electrons, they don't make bonds. Therefore, they're not considered here. Fluorine has the highest electronegativity. Therefore, in this bond, electronegativity difference is calculated 4 minus hydrogen. Hydrogen is 2.51. Therefore, it has a polar covalent bond. So you use electronegativity in the periodic table trends to predict the polarity of a bond in a molecule. So it's important to know the polarities of bonds in molecular compounds. The bond, more electronegative atoms will carry a partial positive charge, delta negative. And the other atom, less electronegative atom, carry a partial positive charge. For example, carbon dioxide. If you look at carbon has higher electronegativity than the oxygen has higher electronegativity. Oxygen is to the right side of carbon. Therefore, oxygen has in the periodic table. So there are polarities, negative polarity, positive polarity in carbon and negative. Now, carbon dioxide molecule is in the overall, it's nonpolar because these are forces. Forces opposite, like a tug of war, cancel each other out. This is pulling this way negative, this is pulling that way. They both equal. In a tug of war, it is not moving anywhere. Therefore, there's no overall polarity in the carbon dioxide molecule. So bonds are stretched or bent in the molecule. If this is so water molecule, it would have an overall polarity. So this kind of a description help us to later discuss about which molecules are greenhouse gas molecules. They are mainly 3 atom molecules. Diatomic molecules don't have any polarity, like oxygen, nitrogen. So we're going to talk about this. Now we're going to look into, to describe the greenhouse gas effect, we're going to look at how different types of radiation is absorbed by molecules. We have UV radiation coming from sun. We talked about that. It breaks up oxygen bonds in O2, UVC. Therefore, it is absorbed by oxygen molecules, removed from entering Earth atmosphere. Infrared is heat, vibration of bonds, stretching bonds, bending bonds. We're going to talk about that in a minute. Microwaves can cause molecular rotations. When you use a microwave, water molecule, do you realize you had to have some water in the food to get it heated up faster? If you don't have water, it's going to take a long time. The microwave absorption by water rotates the water molecules. It creates motion in the food, increase the temperature. Motion is kinetic energy, increase the food. If you look at these three regions, ultraviolet, infrared, microwave, for carbon dioxide molecule, let me go back. Triatomic molecule, ozone, for example, here, this is ozone. Ultraviolet breaks the bond. Infrared, bond vibration. Vibration means bonds are stretching and bending. Microwaves rotate the whole molecule. Do you understand how three different things happen to diatomic molecules? This is water molecule. This is carbon dioxide. This is ozone. Infrared radiation is absorbed by carbon dioxide. Also water. We're going to talk about that, triatomic molecules. About 80% of infrared radiation emitted by Earth is absorbed by atmospheric gases. The carbon dioxide here, water here. This is water, first one. Second one is carbon dioxide. They absorb because they are triatomic molecules. Diatomic molecules don't have polarities. They are equally shared. Therefore, they are not greenhouse gases. Oxygen or the nitrogen are not greenhouse gases. Absorption of IR radiation causes molecular vibration such as bonding and stretching. Only water and the carbon dioxide create that kind of a vibration that could absorb IR radiation. Therefore, they are greenhouse gases. Why do carbon and water vapor absorb but not oxygen or nitrogen? These are diatomic. They don't create polarities when they absorb IR radiation. Vibration are related to shape of the molecule. Triatomic molecules can absorb vibration because their vibration change the polarity in the molecule. We're going to talk about this in a minute. In carbon dioxide, where IR is absorbed, these are the molecular vibrations that are taking place. There are 4 vibrations. This vibration A doesn't change the polarity. Therefore, A is not absorbing IR. but these are unsymmetrical vibrations. They increase the polarity. This stretching vibration, bending vibration, this is bend. These two oxygens bend here upwards and this moves downward. So it's in plane or out of plane. So B, C, D are only one involved in polarity change. Dipole is polarity. No net change in electron distribution in A. B, C, D has change. Therefore, they absorb. Water also has similar situation. We're not going to talk about it. So, carbon dioxide IR spectrum shown in this diagram. There are two absorptions.
Hi, how can I help you? Okay, it'll be right down. One moment.
All right. Somebody helping somebody. Okay. Well, IR vibration in carbon dioxide has two vibration absorption. Can you turn off the mic, whoever it is? Tiffany, you are found on a hot mic. Okay, I turned that off. Okay, if you look at carbon dioxide IR absorption, there are two carbon IR absorption. Therefore, they re-emit infrared heat radiation back to Earth. They are greenhouse gases. Water also have two absorption somewhere around this wavelength. Therefore, water is also a greenhouse gas. So does other greenhouse gases we're going to talk about. Water is not the problem because water has been here for ages. Water concentration is not increasing. They're constant amount. But carbon dioxide is the problem that we're going to look into now. Any molecule of 3 or more atoms can absorb IR radiation and can cause greenhouse gas effect, greenhouse effect. Water is most important gas in the Earth atmosphere, with carbon dioxide second. Therefore, carbon dioxide is the one that is increased. Water is not increased in the atmosphere. It's been there forever. If you look at the Earth, sun's radiation to the Earth, about 46% comes here. Some of them are reflected back here, absorbed by atmosphere, released from atmosphere, reflected from Earth's surface, but only absorbed by Earth, only 37% emitted to atmosphere. 9% just goes away from. Therefore, if you look at this, 46% absorbed, 37 is re-emitted to the atmosphere. Therefore, there's a balance of 46 to 37, about 9% is absorbed by atmosphere. This results in a greenhouse effect. This is where this is needed. If there's no carbon dioxide in the atmosphere, the greenhouse gas not there, our Earth will cool off to -18, which is not a good thing. We cannot live. So Earth temperature is managed at 15 average temperature. So it's a greenhouse gas effect of the carbon dioxide is good and water. But carbon dioxide are increasing and our portion absorbed by the atmosphere is increasing. According to data taken from Mount Mauna Loa, a city in Hawaii since 1958, they found out, this is according to NOAA, National Oceanic and Space Aeronautics, whatever, I forgot exactly what that is. They predict the weather. They are in Florida. So according to this report in Hawaii, since 1960, it was about 320 parts per million, now increased to 400. So that's a lot of increase. What is change in the carbon dioxide in the Earth atmosphere? Make a list of reasons why this should be occurring over this time frame. Breathing and digestion of food create carbon dioxide. Of course, plants and animals take in oxygen and produce carbon dioxide. Production of electricity. We burn a lot of coal and diesel, furnace oil to get electricity, coal burning power plants. Burning fossil fuels emit carbon dioxide. The coal burning power plants continue to increase. They increase the carbon dioxide in the atmosphere. Whether business or pleasure, for business or pleasure, we use a lot of cars and vehicles. Second largest source of US carbon dioxide emission. Industry producing iron from iron oxide use carbon to burn iron oxide, convert iron oxide to carbon with carbon to carbon dioxide and iron. Steel manufacturing. Cement also emit a lot of carbon dioxide when they burn calcium carbonate to produce cement. Deforestation also cut down trees and burn them. So it increases. So we have been sampling carbon dioxide in the atmosphere, and we can use core samples, ice core samples from glaciers in the Arctic region, determine change in the greenhouse gas concentration over time. In the Arctic ice, the weather, there's ice that deposited over a long period of time. They may contain information about carbon dioxide concentration over the time. If you drill into an ice core sample in Arctic regions, in glaciers, you get a piece like this. The bottom one is the past. As you come up to the top, it is the current. So they analyze ice core samples and found out carbon dioxide concentration over a period of long time. increasing over time. Concentration of carbon dioxide is 100 ppm higher than any time in the last million years, 100 times less. So normally, if you look at the ice core data and other data, the 200 is the normal. Okay. It's increased at least up to 300 now, ppm. Now the current data increase shows predicted about 400 ppm, 200 to 300, 400. So we are on the way to increasing carbon dioxide concentration dramatically. So Antarctica, this red is from Antarctica. It can measure up to 800 years back. This 200 years back is from a place called Vostok data. It measured carbon dioxide concentration around 200 years ago. Then Hawaii, Mauna Loa, is the green one, orange one. That shows a lot of increase. That's the current. This is about 20 years. So up to here, it is 300. Now it's predicting it's going to go higher up. Now, if you look at ice core data, we can also from water, we can tell global temperatures. Water has two isotopes, deuterium and hydrogen. When the earth is warmer, deuterium concentration is higher. So therefore, ice core data, if you analyze for deuterium content, there's a series of lines here, shows changes in deuterium concentration. So if you look at this is seasonal variations in carbon dioxide. For putting all these data together, the red one is global temperature in Fahrenheit. The blue one is carbon dioxide concentration from current period to 4,000 years. So it is indicating they correlate with carbon dioxide concentration with deuterium data, where the temperature is measured over a period of time. They correlate with each other. Therefore, there's a direct connection between carbon dioxide concentration and temperature increase. Temperature is measured by deuterium data in ice cores. So we come up with models to create the changes in heat, infrared absorption and reflection from the Earth. So we calculate what we call relative forcing. This is the bottom one, relative radiance. This zero, less than zero, is negative forcing. That means it's not increasing radiation in the atmosphere. Positive radiative forcing is bad. Carbon dioxide create radio forcing about 2 here. Methane, nitric oxide, nitrogen dinitrogen oxide, troposphere ozone also increase the radiative forcing. And land use, black carbon on snow, also increase the radiative forcing. But there are other things like cloud albedo. Cloud also cut down the radiative forcing because Earth is covered by cloud. So that's how I explain. So they consider all these factors of radiative forcing and come up with the model. To explain the temperature increase over 50 years, show both natural and anthropogenic caused by humans. So this is the natural at the bottom. The top line with the black line here is the temperature increase since 1960. Land and ocean surface. This is in only natural forcing. That darker red is natural forcing without any increase in carbon dioxide from fossil fuel. Now these changes are measured by different agencies. One is called Intergovernmental Panel on Climate Change, IPCC, United Nations Environment Protection, World Meteorological Organization, I'm not sure about that. Every 6 to 8 years, they release reports. Now, according to their reports, virtually certain effect of carbon dioxide increase here. Let me go back to it. Upper oceanic increase 0 to 7 meters on the top of the ocean. Let me go back. Warm from 1972, oceans warmed up. There will be more frequent hot and fewer cold temperature extremes over most land areas and daily and seasonal time scales. There will be more frequent hot, fewer cold temperature extremes. That's 99% for sure. The extent of near surface permafrost. Permafrost is ground frozen. How long some places permafrost is frozen ground. That will be reduced. Certain portion of ground is frozen for long time. Permafrost is frozen ground. It will reduce. Global mean sea level will rise many centuries beyond 2100. Extremely likely, anthropogenic influence, particularly greenhouse gases, carbon dioxide and freons and stuff like that, and stratospheric oxygen depletion have led to detectable observed pattern of tropospheric warming. Tropospheric warming is bottom layer of the Earth. And corresponding cooling in the lower atmosphere since 1961. These influence may also have contributed to Arctic sea ice loss. Ice is melting. Since mid-20th century, number of cold days and nights have decreased. cold days and nights. Number of warm days and nights have increased. Heat waves will occur with higher frequency and longer duration. Extreme precipitation over most mid-latitude landmass and over tropical. So regions will become more intense and more frequent. There are going to be a lot of rain in the tropical regions. Turbulent weather. Also, 60 to 100% probability anthropogenic forcing have made substantial contribution to surface temperature increase since the mid-20th century. Anthropogenic influence have affected global water cycle and retreat of glaciers since 1966. Over the second half of the 20th century, there were more land regions where number of heavy precipitation even had increased than where it has decreased. Precipitation is because of the heat in the atmosphere. Water condense and may create rain and get evaporated, and it happened more frequently. Ocean warmed at the depth of 700 to 200 upper layer between 57 and 2009. Even below bottom between 1992 to 2005, recently, bottom ocean layer. Tropical oxygen minimum has been detected and it is expanding. In tropical region, oxygen levels are going down. The global mean surface warming is in the range of 0.5 to 1.3 over the period of so temperature has increased. Unlikely, but 0 to 33 probability relative to 1859, the 1900, 1850 to 1900. Global temperature, surface temperature will in the 20th century, 2081 to 2000, will increase by 2 Celsius degrees. Now, these are the conclusions. Arctic is declined, ice 9% over decade. Oceans are warming, ice is thinning. Solar energy is absorbed by water. The ice reflects some of the radiation, but water absorbs. Then it causes more melting. These things can change the temperature of ocean layers, impact ocean circulation, salinity, change marine habitats, and widen shipping lanes. They all contribute to more pollution. This diagram shows how the Arctic ice caps have melted over the period of time. 30-year average sea ice minimum, yellow line, is the original line. So we are reducing our ice, Arctic ice. This will affect coastal sea level rise. Coastal area is in danger. More extreme weather, severe storm, drought, flooding, etc. Changes in oceanic chemistry, change habitat and extinction. Vulnerability of freshwater resources. We can get spread of diseases like malaria, cholera, because of the flooding contaminate our water with pathogens. The IPCC certified scientific basis for the greenhouse gas effect. So after we came up with the idea that greenhouse gas causing radiative forcing on Earth, people got together, governmental organizations got together and come up with Kyoto Protocol in 1997, reduce atmospheric greenhouse gases. Emission target set to reduce emission of 6 greenhouse gases from 1990 level. Carbon dioxide, methane, nitric oxide, nitrogen oxide. New refrigerating chemicals, hydrofluorocarbons. We use hydrochlorocarbons. That's gone, but still HFCs are greenhouse. Perfluorohydrocarbons and SF6. All these has to be reduced. We give incentive to power plants, cap and trade agreement. If they save emissions, if they reduce emissions, they get benefits. So we are trying to force industries to pay for emissions. So there will be more incentive to carbon dioxide emission reduction. Now we are almost at the end of it. You form a group, talk to other people based on your current knowledge. Do you feel greenhouse effect and warming of the atmosphere is good or bad? It's in a way good, but too much carbon dioxide create more problems now. Where does the carbon dioxide in the air come from? We talk about different ways we can produce carbon dioxide. Production of electricity, transportation, deforestation. We talked about that. What is climate change? So it is mainly global warming, melting of ice, sea level increasing, turbulent weather. They are all reflected in carbon dioxide concentration and the green warming of the atmosphere. Is climate change occurring? You guys still believe it's kind of a politicians paid by fossil fuel industry are not going to admit climate change is occurring? Compare your answer to those from part of the start of the chapter. When you start going through this chapter, what was your opinion about climate change? So we are done with chapter 4. I'm going to stop the class at this point, and we go review on next Thursday, Monday and Wednesday. Then we have the test week after. 2 more days to discuss answers to questions in chapter 3 and 4. Do you have